Question 4. A body of mass, m, is moving along a smooth horizontal track with an initial speed of 3u. It collides elastically with another body of mass 2m, which is initially at rest. After the collision, the first object rebounds, retaining 1/9 of its initial kinetic energy. What is the final speed of the object of mass 2m after the collision? This question tests our understanding of elastic collisions, particularly how kinetic energy and momentum are conserved during such interactions. What are the major ideas involved in solving this problem? We know that in an elastic collision, both the total kinetic energy and the total momentum of the system are conserved. This means the total kinetic energy and momentum before the collision must equal those after the collision. For all collisions, the total momentum before collision equals the total momentum after collision. This is expressed mathematically as below. Another important idea is that direction matters. If a body rebounds after a collision, its velocity reverses direction, so its final velocity must have the opposite sign compared with its initial velocity. Now, let us work through the solution step by step. First, we calculate the initial kinetic energy of the body of mass m. The kinetic energy formula is 1/2 mv squared. The initial speed is 3u, so the initial kinetic energy becomes 1/2 m multiplied by 3u squared. This simplifies to 1/2 m multiplied by 9u squared, which gives 9/2mu squared. Now we are told that after the collision, the object retains 1/9 of its initial kinetic energy. So the final kinetic energy of this object is 1/9 multiplied by 9/2mu squared. This simplifies to 1/2 mu squared. Now we use the kinetic energy formula again, this time in terms of the final speed v1, to determine the final speed of the object of mass m. Thus, 1/2 m times v1 squared equals 1/2 mu squared. The masses m and the 1/2s cancel out, leaving v1 squared equals u squared. Taking the square root gives v1 equals plus or minus u. However, the question states that the object rebounds, meaning it changes direction, or reverses, so its final velocity must be negative relative to its initial direction. Therefore, the final velocity of the first object is minus u. Next, we apply conservation of momentum. The total momentum before the collision must equal the total momentum after the collision. Before the collision, the object of mass m moves with speed 3u, while the object of mass 2m is at rest. So the total initial momentum is m multiplied by 3u plus 2m multiplied by 0. After the collision, the first object has velocity minus u, and the second object has velocity v2. So the total momentum becomes m multiplied by minus u plus 2m multiplied by v2. The left-hand side simplifies to 3mu, the right-hand side simplifies to minus mu plus 2mv2. Moving mu to the left side and adding gives 4mu equals 2mv2. Dividing both sides by 2m gives v2 equals 2u. So the final speed of the object of mass 2m is 2u. This is our final answer. What did we do? First, we calculated the initial kinetic energy of the moving object. Then we used the information that it retained 1/9 of this energy to determine its final velocity, remembering that it rebounds, so its velocity becomes negative. After finding this velocity, we applied conservation of momentum to determine the final speed of the second object. A useful tip here is that since the first object keeps only 1/9 of its kinetic energy, the remaining kinetic energy must be transferred to the other object that was initially at rest. Here is an alternative way to approach the problem. Since the first object keeps only 1/9 of its kinetic energy, the remaining kinetic energy must belong to the object that was initially at rest. This is because, since the collision was elastic and no kinetic energy was lost, that means all the total initial kinetic energy must have been shared only between the objects. As we determined, the total initial kinetic energy, all of which is from the body of mass m, is 9/2 mu². Also, after collision, this object keeps 1/9 of this total initial kinetic energy. Hence, the second body's kinetic energy after collision is just the difference between the total initial and the final for the first object, which then gives 8/9 of the total initial. Substituting the expression for the total initial gives 8/9 times 9/2 mu². By simplification, this gives 4 mu². We then write an independent expression for the final kinetic energy for the same second object of mass 2m in terms of its speed, say v. This is 1/2 multiplied by 2m times v². This should equal the equivalent in terms of u, which was 4mu². Simplifying gives v² equals 4u², and by taking the square root of both sides, gives v equals 2u, just like we already obtained before. This has provided an alternative way to approach the same problem. Let's recap on the main ideas in solving this problem. In an elastic collision, both momentum and kinetic energy are conserved. The statement that an object rebounds means its final velocity is opposite in direction to its initial velocity, and must be treated with a negative sign in the momentum equation. And finally, maintaining a consistent sign convention is essential when solving collision problems, as incorrect signs lead to errors.